Welcome back to our series exploring the Meyer Fire Tool Kit. In developing this series, it's our hope at MeyerFire that you're able to see the inherent value of the Meyer Fire Toolkit offers you and your team as a time-saving tool that allows you to spend less time doing research and more time doing the work that helps your efficiency. This is a tool that I personally use quite often, and we hope you see its value. In our last segment, we looked at the MeyerFire Toolkit Sprinkler database. In this segment, we're going to work through the Sprinkler K-Factor Selector function. The Sprinkler K-Factor is a pretty important consideration, but its overall importance is easy to overlook. Unless someone is a sprinkler designer, the concept of K-Factor is frequently misunderstood. If you had a chance to explore any of our courses involving automatic sprinkler system hydraulics, you already know that the Sprinkler K-Factor is a critical element of the system calculations, as the K-Factor is a coefficient that directly relates to the orifice of the sprinkler. Choosing the right K-factor in the design portion of a project can not only impact the hydraulic efficiency of your design, but can also affect the economics of the overall project. Basically, it takes less pressure to get the same volume of water through a larger orifice than a smaller orifice. I joined my company in 2017 as the Design and Engineering Technical Director. Prior to that, the company focused primarily on service and system modification projects, but wanted to jump into more design build to take advantage of the growth in Central Texas. I can vividly recall numerous cringeworthy conversations early on where staff referred to sprinklers by their thread size, half-inch or three-quarter inch. There was a universal, albeit grossly incorrect assumption that all half-inch thread sprinklers were standard coverage and all three-quarter-inch thread sprinklers were extended coverage. So, after trying not to think about all of the service or modification projects in the past where potentially incorrect sprinklers may have been added to a system, I spent quite some time explaining the importance of Sprinkler K-Factor. Now, several years later, our field superintendents refer to sprinkler devices by their K-Factor, not their thread size. As we open the K-Factor Selector tool, we immediately see some dialog boxes near the top and then a pretty big color-coded chart below. The dialog boxes default to ordinary hazard group 2 design, referencing sprinkler coverage at 130 square feet and a required density of 0.20. The fields below the dialog boxes in the chart are not editable, but rather provide information to you based on your inputs above. The coverage area is the amount of area each sprinkler protects. This is per sprinkler. A higher coverage area means less overall sprinklers in the system, but also means a higher required flow for each sprinkler. Likewise, the inverse is true. A smaller coverage area per sprinkler means more sprinklers on the system, but can meet the needed density with a lower flow to each sprinkler. 130 square foot sprinkler coverage is our maximum allowable for ordinary hazard groups 1 and 2 using standard coverage sprinklers. In my practice, I have a standing directive for my design staff to try to avoid this maximum coverage for ordinary hazard designs because if we run into issues in the field, we don't have enough margin to move any sprinklers. So generally, we try to use 120 square feet coverage, but that's just me. For this example, let's select 120 square feet as our coverage area. This next editable box is for design density, which is the density required to protect the hazard. This is the amount of water our system needs to discharge through the sprinklers within the hydraulic remote area. The presumption here is that the designer has already determined the required density from NFPA 13. Selecting the design density is the next step in populating the information we'll see below. So for this example, we're going to stay with ordinary hazard group 2 and set the density as 0.20. The box below coverage is global flow. This box is not user editable, but is rather calculated based upon the inputs in coverage and density. This shows us the minimum amount that each sprinkler must flow to achieve the density we need to achieve. With the adjustments we made to coverage and density, we can see that we need to be flowing 24 gallons per minute from each sprinkler. In the table below, we see a list of K-factors. What we will see looking to the right in this table is the minimum pressure required to achieve the minimum flow rate needed to attain the density we input earlier. The column to the right of the K-factor column shows us the minimum pressure. This will never be lower than 7 psi because NFPA 13 shows us that 7 psi is the minimum operating pressure of any fire sprinkler. Even if the calculated pressure needed to meet the demand of our system is less than 7 psi, the required minimum pressure of 7 psi will always govern, and this column will always reflect that. In those cases, it just means that we'll have a higher flow rate than the minimum required. However, some sprinklers are required to operate at a higher pressure, and in some cases, much higher. Extended coverage, ESFR, control mode special application, and other special application sprinklers often require higher pressure. In the case of ESFR and control mode special application sprinklers, that minimum operating pressure is found in the design criteria within NFPA 13. For extended coverage and other special application sprinklers, that data is typically found in the manufacturer data sheets. The next column is dynamic in that it changes based upon our earlier inputs. This shows us the minimum pressure each sprinkler must be supplied with to meet our system density requirements. As we discussed earlier, it takes higher pressure to get the same volume through a smaller orifice sprinkler than it does through a larger orifice sprinkler. Larger K-factor sprinklers lower the required pressure, but as we just learned, it can never drop beneath the NFPA minimum requirement of 7 psi. With the values we put in earlier, we can see that to achieve the required density of 0.20 with 120 square foot sprinkler coverage, a K5.6 sprinkler needs to be supplied with at least 18.4 psi. Comparing that to the K8.0 sprinkler immediately below, we see that only 9 psi is needed. While we're here, take a look at the K11.2 sprinkler immediately underneath the K8.0 sprinkler. This sprinkler only requires 4.6 psi to meet our density. But remember, a minimum pressure of 7 psi is always required, even though hydraulically we can get the density of 0.20 with less. One more thing I need to add is that even though a lot of K11.2 sprinklers are listed for extended coverage, we set our sprinkler coverage at 120 square feet. The next column we're going to look at is actual pressure required. This is similar to the previous column, but it accounts for the NFPA required minimum pressure of 7 psi. When we leave all of the user-selected parameters as they are, we can see that every sprinkler from the K11.2 sprinkler on is green and shows 7.0, even though the previous column, minimum pressure to satisfy density, is less. This is what we refer to as the controlling pressure. The next column to the right shows the actual flow per sprinkler resulting from the actual controlling pressure we just discussed. This is presented as a sort of bar graph visual indicator. As we can see, the actual flow increases with the higher K-factor sprinklers due to the larger orifice sizes these sprinklers offer. When we're flowing more water than is necessary to meet our required density, we refer to that as overflow, sometimes referred to as overage. The final column is really the meat of this particular tool. Once again, we have the same parameters we've been using. As we look at this column, we see two identifiers labeled pressure and flow. For the density and sprinkler coverage we have selected, we can see that the K8.0 sprinkler is the most efficient for our flow, while the K11.2 sprinkler is the most efficient for our pressure. This is designed to help us choose a K-factor that matches our goal. If we want to minimize the required pressure, we would want to choose a sprinkler with a K-factor that keeps us at or near the minimum pressure. In this case, the K11.2 sprinkler has the lowest starting pressure at 7 psi. If we want to minimize the overall flow, we want to choose a K-factor with the least amount of overflow. In this case, that's the K8.0 sprinkler. The sprinkler K-factor has the lowest amount of overflow coupled with the lowest starting pressure of K-factors on the lower side of the flow spectrum. If you've taken any of our courses examining water supply, you know that we need to trade pressure for flow and vice versa. Higher K-factor sprinklers will lower the starting pressure needed to meet the required density, but can increase the overflow. Lower K-factor sprinklers do a great job at minimizing overflow, but require a higher pressure. The systems we design use the available water supply as their foundation. If your water supply doesn't have the greatest pressure, then using a sprinkler with a lower starting pressure may help optimize your calculations. If your water supply has volume problems, then choosing a sprinkler K-factor that minimizes overflow may be your better option. In this segment, we explored the K-Factor Selector in the Meyer Fire Tool Kit product. We looked at the user-selectable areas for choosing sprinkler coverage area and required density. We looked at how the toolkit then populates the elements in the chart below for minimum flow and K-Factor. We looked at the minimum pressure allowed by code, which is always at least 7 psi, but may be higher for some sprinklers. We explored the minimum pressure needed for each of the sprinkler K-factors to meet the density we have selected. We discussed the actual pressure required for each sprinkler K-factor to meet that density, as well as the actual flow that will be produced. Finally, we discussed the optimal sprinkler column that balances the pressure and flow. I'm Jesse Cecil. This is Meyer Fire University.
This has been a preview of Meyer Fire University. Join the next generation of fire protection experts at www.meyerfireuniversity.com.